Yay, thank you. Welcome, everybody, to our repository data mining on GitHub talk. My name is Johannes Nicolai. I'm part of GitHub's Enterprise Solutions Engineering team, and I'm really, really honored to be here on behalf of GitHub and sponsor this amazing conference. Talking about sponsoring, you should all have received a voucher from GitHub. If you enter that one into github.com/redeem, you actually get 1 month of free, unlimited repositories private on GitHub. If you are a developer, you can also get the student developer pack where you get this for the entire tenure of your study. Before we dive right into the heart of this presentation, data science, machine learning, I just wanted to do 3 warming up questions. So first of all, that should be an easy one. Please do raise your hands if you are using GitHub in some form already. Yay, that's almost everybody. Awesome. So we will do some little bit more complicated question now. The picture you can see here shows 4 gentlemen. Do you have any idea who they are? Just shout it. I don't know what names, just their function. The founders, exactly. These are the GitHub founders. So that was easy answered as well. And there will be a third really, really hard one. And the first one who can actually answer that one will get a gift card for the GitHub shop after this talk. So what was the name of the company those 4 guys founded originally? And hint, it was not GitHub. Any ideas? 10 seconds. 5 seconds. So the company was not called GitHub. It was actually called Logical Awesome. That's right. That is GitHub's original name. The reason for that is that actually the idea of our founders was not to program GitHub. They had an entirely different idea. It's just that they developed GitHub to collaborate with each other, right? They just wanted to have a nice UI around Git. And this is what attracted all those open source projects you probably now are aware of. This is why you're using GitHub in the first place, right? We, for instance, have the MXNet machine learning framework from Amazon hosted on GitHub, or TensorFlow from Google, or Python and scikit-learn, and many, many other amazing open source technologies. Actually, there's 50 million repositories on GitHub which are open source. But apart from that, there's also many, many other commercial software development going on GitHub from companies like Uber, Lyft, Facebook, or Austrian, Swiss, German companies. And if you want to take GitHub to work, if you want to use the system yourself as well, that's possible even if you can't go to the cloud. If you want to install it on your own computers in your own data center, that's possible too. If you're interested, just catch me after the presentation. But this is not a marketing talk. This is about machine learning at GitHub. Right? And I'm not sure whether you guys are aware, but there is a recent publication from O'Reilly with compliments from GitHub. It's free. It's maybe 25 to 30 pages. And it actually shows what is going on behind the scenes. The data science process of our machine learning team, the tools we are using, but not just GitHub. It's also about Scotiabank. It's also about Airbnb. I will just keep that slide on the screen for a couple of seconds so that you can take a photo in case you're interested. As I said, it's a free publication. But there's also many things not going on behind the screen, but on the screen. Features which are already showcasing machine learning on github.com. Take topics, for example. Anybody of you heard about topics? Hands up. Yeah. Maybe 10%. So basically now GitHub can predict the nature of your repository based on the content and its activities. So take the Atom editor, for example. You will see that GitHub correctly predicted it's a text editor, it's Atom, there's multiple operating systems supported, and it's written in JavaScript. And if you predicted something wrong, then the project owners can just say, this should be the right categorization of things. And this knowledge is then fed back into our neural networks. So we have about 50 million visitors every single month, unique visitors, and all their intelligence, the swarm intelligence, is used to improve GitHub and bring out exciting machine learning-based features like this more and more. So stay tuned for the new announcement at Satellites. While this topics feature was developed, a parallel challenge was going on, the Informatik Cup. This was a competition conducted by GitHub and the German Association for Computer Science for students of Austrian, Swiss, and German universities. It was a 5-month competition, which was really similar to topics, The only difference was instead of coming up with an arbitrary amount of classifications, you had to classify any kind of repositories into 7 predefined categories: development, education, whether it's a homework repository, whether it's documentation, whether it's a data-driven project, whether it's GitHub Pages, or whether it's something else. And the team which actually won the Best Presentation Award in the final round of this GitHub Gesellschaft für Informatik Machine Learning Science Challenge, wow, that was long, is with me on stage today, Fabian, Tobias, and Maxim, and I will just hand it over to them without further ado so that they can show you how they tackled that problem in the competition. Thank you.
Yeah, thank you for the introduction. Thank you for the introduction, Johannes. And before we dive right into the task, a quick word about ourselves. We are all students, undergraduates at the University of Osnabrück in Germany and studying cognitive science. So let's start. How could you go about classifying repositories? Well, you could try to look at the code, but we decided pretty quickly against that because, well, analyzing code is hard. That leaves us with metadata. We have the number of branches, stars, follows, commits, all these numbers that repositories are associated with them, and we could use these to do classifications. There's also text data, the README and commit messages. You could use these. And if you now want to build a classifier from them, you have a huge toolbox to choose from. There's support vector machines, decision trees, random forests for metadata. For text classification, common approaches you may know of are back of words or TF-IDF. But we want to talk about something different today, because we actually use the deep learning approach for text classification and applied this to READMEs and commit messages. A quick show of hands maybe. Who has heard of StanzaFlow here and used it maybe? Who has worked with Word2Vec? And who thinks regular expressions are enough for all their text analysis needs? Well, that's great, because in the rest of our talk, we're going to walk you through this pipeline we used and explain about the different steps in it and some of the intuitions behind using such a technology. In a quick overview, we start out with the README, or the commit message of this text, separated into all the different words in it, and then we look these up in a guide lookup table. That's what Word2Vec essentially is, or you can see it as such, and it gives you a semantic representation of your words in form of a high-dimensional vector. Now that you have this representation, you can use it and feed it into a neural network that we developed with TensorFlow. And this neural network is trained then, if you have to give it this representation and labeled examples of repositories, and it learns to detect patterns in your text. And from these, outputs a calculation. You adjust it based on the errors it makes, and then, if you're done with training, you have a classifier. So, why should you care? Well, we found this architecture to be really easy to use, robust, and it has great performance on a variety of different datasets and tasks, ranging from things like sentiment analysis to question classification. So let's start with the first step of our pipeline, Word2Vec. Why do we need a data preprocessing step? Well, basically all machine learning algorithms operate on numbers. And we have to transform our words into this numerical representation. A simple way to do this would be just assigning unique IDs to each word in our vocabulary. This could look like this. So you assign vectors to each word, and you essentially have a high-dimensional space that has as many dimensions as you have words in your vocabulary. You might do this in a bag-of-words approach. And that works fine on some problems, but with this approach, you have no semantic information about the relationship between words. And that's what really matters about words, isn't it? They have meaning associated with them. And we don't want our classifier to learn this specific to our data set. We actually wanted to start out with this meaning, an intuition about how these words, what these words mean. Words are just symbols, essentially, and what really I care about is the intuition, the concepts behind them. So we can do something different. We can use conceptual space, very high-dimensional space that has these vectors of words in them. It carries semantic meaning. And we can operate on these vectors instead of just on symbols. And that allows us to do something more powerful. Let's look at such a conceptual space and an example of how it might look. You might develop a simple conceptual space for animals. And your dimensions in this page actually correspond to features. Meaningful features like here the number of legs and the cuteness of the animal. So the octopus probably would be down there. High leg count, low cuteness, seriously. And cats could be up there. Octocat, maybe there. This is really a simplified example, and in practice, you might not be able to build a conceptual space that fulfills all the criteria you may see in various research papers about conceptual spaces, but it's still pretty useful. What we essentially end up with is a space that has a few hundred dimensions only, boiled down to the essentials that we can use. And we construct this by making a few assumptions and then going over a huge corpus of actual users of language and extracting these vector representations. More about that later. Let's look at what we get out of this. Well, similar words are commonly clustered together in this conceptual space. So that already gives you a huge advantage that you don't have with back-of-words approaches. And you can do some other nice things, like analogical reasoning. That just means that words, or pair of words that share some relationship are all positioned similar to each other in the space. You might think of some of these pairs of words, pairs like king and queen, or man and woman. These are just variations in gender, and that's the common relationship they share. And then you can do actually arithmetic with words. That's what we want for our for our machine learning algorithms, because they operate on numbers. And now they can operate on words just like numbers. It's not an exact science, but it works and it helps in classification. So you can take king, subtract man, add woman, you basically swap out the gender part and end up with queen. Some other cases where this might work are verbs in their different tense forms, and capitals and the corresponding countries. They all are positioned similar to each other. And we can show you now a visualization of how such a conceptual space might look like in practice. This is a two-dimensional projection of the conceptual space, because, as we have learned, it's very high-dimensional, and we don't have really much imagination how it looks like. But TSNE, an algorithm for this projection, tries to project it into 2D and keep some of the structure that we have in the space in this projection. So let's look at what relations we can find.
Well, let's see what we can find in this space. Let's zoom in here and take a look what we can see here. So here we have combined growth, increase, demand, interest. So this seems somehow growth semantic seems to be encoded here in this region. Or here we have construction, building, build. So in this region of the space, we have construction and building semantics encoded. This is exactly what we were talking about, this clustering of similar semantics. But we promised you a lookup table, didn't we? And now I'm going to talk about how to actually build such a system. And one implementation of that is WeAreDevelopers, an open source project by Google, which does exactly create such a word embedding. And yeah, before we can get started with that, we have to go back to linguistics for 1 second. But we only need one simple hypothesis called the distributional hypothesis. It just says that words with similar meanings appear in similar contexts. So take, for example, the sentence, the fluffy something is sleeping. You would expect to hear dog or cat here. So the fluffy dog is sleeping. The fluffy cat is sleeping are valid sentences. The fluffy octocat is sleeping is as well. But the fluffy car is sleeping is obviously nonsense. So in general, all words that could fit the sentence are very close semantically. So they are cute little animals. Now, if we go back to conceptual spaces, we can rephrase this hypothesis a little bit. We can instead say that words that are close in a conceptual space appear in similar contexts. And this is something we can work with. This is something we can build a machine learning system with, actually. We can define a simple learning goal or objective function for a machine learning system, which just tries to predict the word that was left out here. So from the fluffy something is sleeping, we want to predict cat, or want to predict dog in another example. And we take this example from some very large body of text. For example, the entire Wikipedia, Google News, something like that. So really a lot of data. And then we take a simple machine learning system, a two-layer neural network, where in the input layer, you just sparsely encode your context. Sparsely encode just means we take these IDs. So we assign some arbitrary values to the words, which carry no meaning. Then we have one layer where we have some complex hidden representation. And finally, we have an output layer, which is just, once again, sparsely encoded. And then we train this on our data set, on the entire Wikipedia, and we have a lot of sentences like, the sun is shining today. Now, we feed this sentence into our network, and it takes this context and activates some internal representation of it. This is the second layer you saw. And now it has to predict from this representation the target, shining in this case, in the easy case. In the harder case, for example, the fluffy something is sleeping, it could be either dog or cat that it has to predict. So it has to learn that from this representation, it could map to either of those words, which has the effect of moving those words closer together in the internal representation, while moving words that cannot occur here farther away. This was exactly the property we were looking for in order to construct such a space. And once we are done with training, so we trained it for a long time on the Wikipedia, we can just reverse this last step and use these target IDs that we defined arbitrarily to look back up into this hidden complex representation. And these exactly are our word embeddings, the ones that we can work with. Now, if you want to use this just to include this semantic information in some machine learning system, you do not have to go through all these steps and train them yourself. There are actually very good pre-trained implementation available. For example, once again at Google, with Richters trained on the entire Wikipedia, Google News, whatever you want. But if you have some exotic data set, you might want to train them yourself still. But with that, we can tick off the first part of our pipeline. We took our text, which was encoded just in words, found a numerical representation for it, and included a lot of semantic information in this representation. So now we have some high-dimensional space, some high-dimensional representation of our data. Now we want to do the actual classification. And for that, we are going to use a neural network, specifically a convolutional neural network, which was a very prominent approach in recent years for working with high-dimensional data. Specifically, it was very prominent for working with image data. And one framework you can implement this with, and this is what we used in our submission for the project, was StanzaFlow, which is once again Google's deep learning framework, which they use internally, but is also open source. So it has a very high quality, and you can do good stuff with it. But let's go back to the convolutional neural networks. Why do we care about something which is good on image data? There are a lot of similarities between working in 2D space and higher dimensional space, but you can make pretty pictures with 2D space, so let's get started. These convolutional neural networks are made out of convolutional layers. What these do is try to extract interesting features, properties, patterns from their input. So, for example, you put in this cute little octocat in there. And what you get out are all kinds of interesting things. For example, you might get outlines, or you might get all bright colors detected, or that one up there detects tentacles. So you just extract features from this image. And you stack multiple of these layers on top of each other. So you now have other layers which extract features from these features, and you have layers that combine these features. You keep stacking them, and at some point you have a deep neural network which can actually do classification. Now you let it do classification and put in real images. And Now you can try to visualize why it made that classification. So for example, you see here a bird which was classified as a bird, as a flamingo. And it was classified as a flamingo because of its long legs and its long neck. Or the spider was classified as a spider because it had this characteristic legs of a spider. Or this cute little cat was misclassified as a ferocious tiger because it had vertical stripes and this typical face of a cat. And so we can kind of guess that what this network learned through all these stacked convolutional layers is to combine these simple features into representation of patterns that correspond to these animals somehow. So it learned that tigers have vertical stripes, which are characteristic for them. We can actually go one step further than this and try to visualize what exactly this network is looking for. And this you can see here. These are sharks, ostriches, robins, and lizards. But wait, those aren't actually ostriches, are they? So you do not see one typical ostrich here. But what you rather see is just some pattern splattered all across the image. You see a lot of long necks, a lot of long beaks. I don't know if you can see this good on the projector, but basically what this network learned was that ostriches have long necks, but it has no concept of an ostrich itself. It just found patterns in your data which somehow correspond to ostriches. And it looks like this for 2D case, but the same holds true for data of any dimensionality. And this is what we get to now. And Tobias will tell you more about that.
Thank you. But before we can start with text, we have to first understand how the convolution actually works and the operation behind it. And for this, we look at this black and white image here, and we see that what convolution actually is a sliding window function. So we slide such a filter over this image, and what we get out here is this activation pattern here on the right. And as you have realized by now, this specific filter with these specific weights is actually detecting vertical edges. So if we do this on real images, we will detect just that, vertical edges. And we can do this with all kind of edges, not only vertical ones. We can do this with colors. We can do this with shapes. And these are the images that you've already seen that Maxim showed you. And now let's do the transition to text. What we do there is exactly the same thing. We slide such a small window over the whole text, over the whole sentence. And the only difference now is that your text is one-dimensional data, and your pixels are basically words. Well, there is one important difference between images and this text. And what we had in images were color values and pixel intensities. And we do not have something like this here. I mean, what is the color of a word? Nevertheless, we need numerical features to do our calculations, to perform our convolution. And wait a sec, we've actually talked about this already. We have those word vectors that allow us to transform words into vectors. And with these word embeddings, all the nice semantic features that we've talked about come for free. Now, still the question arises, which features do we actually detect in the text? And sadly, we do not have these nice intuitions that we had in the computer vision case, where we had edges and shapes. But certainly, we will consider word order in here, which we neglect in other models, like in a bag of words model, for example. And what we also detect are certain groups of words which belong together, like the quick brown fox, which is one noun phrase in this sentence. And now that we have those features, these groups of words, interesting groups of words, are now our features. And we have the semantics along with it. Now we can do text classification. And for that, we need a whole convolutional network. And once again, our words now are here on the x-axis, and on the y-axis, we have the corresponding vectors. And this builds then our input matrix. And on this, we can do our convolutions. So we slide our filters over the words and cover the whole vectors. And what we end up with is a whole bunch of features here with different sizes and with different variations. And these features now basically tell us, I have found an interesting group of words here in the text. I have found another one here below here. And we do want to do text classification, right? So we do not care that much about the location of those features, but rather only if they occur in the text. So we can drop some information. And this is done by this pooling layer, how is it called, which basically performs the dimensionality reduction. So we have very small feature vectors, and with those, we can actually do our classification by training the last layers of the network on those features and get the categories which we are after. So for training, we actually need many, many samples of text. In our case, to come back to the competition, we need the repository content, the readmes, and we train now the network. That is, we propagate this text through the network, and in the beginning, it will, of course, make large errors. But as we give the network a feedback of this error and iteratively adopt these filters here, basically, we can train the network to a sufficient degree and where we say we are happy with this now. So we are done with our next step. We have done text classification. And what we finally want is we want our categories from the competition. We want our development, homework, or web and data and so on category where we can say this is the category of our repository. And let's say, let's look at how we implemented this in our architecture. And for this, we actually used two CNNs. One was fed with data from the README. The other one was getting data from the commit, of course, in the vectorized version. And then those two CNNs give us an individual voting for our final classification. And in order to combine them, we use something like an ensemble layer, which does nothing special, but just weights these votings and gives us our final classification, our final category. So we say we are 80% sure this is a development repository. Something like this. So that's it to the project. If you got interested, check out the Informatik and our submission. And if you even want to get started with deep learning on text on your own, we have prepared an IPython notebook for you where you can interactively train such a network as we used and see how these word embeddings actually work. Finally, also, you find the visualizations or the code from the visualization in this last repository. And you can see how this computer vision actually works once again. So for now, thank you for your attention. And if you see us around, feel free to ask us any questions.
Thank you. This was an amazing talk. There are no questions. Maybe because the internet is down, but probably you have answered everything. There are no questions left open. But let me ask a question. How was it working with GitHub? How close was the collaboration on that project?
I guess we can describe it from our perspective and from GitHub's perspective. So this competition was not only carried out by GitHub, but GitHub was one of the main sponsors. But it was actually carried out by the Gesellschaft für Informatik, which is a big organization in Germany for informatics or informatic competitions also. And they were the hosts of the competition. So what GitHub provided were, I think, the problems. So the problem statement itself was written by GitHub, but other than that, it was very much to our own discretion how we work on this problem. So we did not get any data set or were guided through this problem, but rather we were just left with the problem and they wanted to see how we work on it.
So he's right, it was a combined effort of Gesellschaft für Informatik and GitHub. The task itself was published on using GitHub pages, so when you want to host static websites for free, you can use GitHub for that. Almost every single team was using GitHub for submissions, and while there were many questions from many teams, those were answered in issues, right? And sometimes even after the final submissions got in, some projects did not work from the very beginning. So we got the chance to ask and add some pull requests to it. And at the end, every team also had the chance to add pull requests to the GitHub pages to present their final results. So if you visit that GitHub page, the very first, well, it's not on the screen anymore, it looks like. If you Google for Informatik and GitHub, you will find also the results of all other teams and how they got to their solutions, including all the steps in Jupyter, IPython notebook. So was pretty awesome.
Thank you very much, gentlemen.